What's going on, everybody? So figured out that I wasn't recording when I did 4 through 11. So here's what we're going to do instead of me redoing the entire thing. I'm just going to quickly show you the solutions, talk through them real quick, and we'll just do that. Okay, sounds good. Awesome. So seeing here, this is just a quick find the equivalent capacitance. Remember, we have flipped rules from the resistances. So here we can see that this series is going to have the 1 over C3 plus C4. Find our series value. Once we find that series value, it'll be down here. Combine that to there. And then 1, 2, and 3 will be in parallel. And since they have flipped rules, we can just add those values together, and it'll give us that equivalent value. Nothing too nuts. Okay. Moving on to the inductor combination. So here they ask us to find the equivalent inductance. So we see here we have a series, and since these have the same rules as the resistances, right there, we just add those two values together. Once we combine that down to L series 1, we'll see that these two are in parallel. Use that equation there. Then we'll combine that down. Then we have another series here. Combine it there. And then see this last little bit is in parallel. It gives it right there. Okay. All right. So we'll look at our circuit here. So this circuit originally had a capacitor here, voltage source, a resistance, and the switch. So we can see from the switch initially it was open. So since it was open here, this capacitance voltage was initially at 0. You can see here from stated, initially 0 charge. But then at times it goes to infinity, it flips down, and then that goes into closed, which is what we had here. So if we closed it off, we'll let that run to infinity. So we can kind of see that there's a charging discharging equation going on here. Have our voltage value initial. Don't know what this is quite yet. And we need to find our tau from our equations down here. Okay, so if we let time run to infinity, that capacitor is going to open up to be clipped out. So right there. Yeah, so time goes to infinity. And to determine that V of C, what we can do is run this current through here, or we can walk around here. So voltage source, no current is flowing through that resistance. So because no current's flowing through there, it won't absorb any voltage. Okay. So it has 0 voltage. But then coming down through here, V of C, so plus minus, plus VC. And we'll end up back where we started, so equals 0. So V of C is equal to V of S at time goes to infinity. So we have V of C infinity. That's how we found that. Okay. So then all we have to go do is run through here, and we see that we have V of L at infinity, or V of C at infinity, V of C initially. We have our time. We just don't have our time constant tau. And remember, time constant tau for capacitors R times C. So the reason why we kind of got a lot of practice with the Thevenin and Norton is because we'll take our sources, zero them out, and then we'll find our R equivalent, like we were doing with the Thevenin and Norton. So we're going to take it with respect to that battery, VC, right here. And we see we only have one resistance, so that resistance is our R equivalent. We'll plug that into tau. Tau is equal to 40 kiloohms times 5 microfarads. Multiply those two together, and that'll give us 0.2 seconds. Unit for time constant is seconds. Okay, so then we have all the pieces of information we need. We can just take all that jazz and just plug them into here. And 500 milliseconds is the same thing as saying 0.5 seconds. And that's all we need to do for the charging and discharging equation. Let's write that out right there. So I'll put a star by this one. This one's very important. I would know this one very well for your test. Ooh, excuse me. So it says, in an RC circuit where they give you a resistance value and the capacitance value, so these two values here. An RC circuit is just resistor capacitor circuit. The capacitor is fully charged at time is equal to 0. How long does it take the capacitor to discharge to 30% of its initial charge? Okay, so what that means is that it's discharging. So we got to use our discharging equation. So we'll go and write that out. So looking at this, we don't know what the actual value of V of C initial was. They didn't say what the actual voltage value was for anything. So we're not quite sure on that quite yet. But we know that if we're discharging in a capacitor and we let it run forever, it's going to discharge to 0 volts. So we can send both of those to 0. Okay? And now let's look at our tau. So our tau is equal to RC. All right? And they give us R and C. Take those two, multiply them together, and we now have our tau. So we can go and update our equation. So V of C at time is V of C initial e to the minus t over tau, where we now have, we now have tau. Okay, but we still don't know initial voltage. We don't know voltage at a time either. But they're asking for 30% of the initial voltage at a time. So what we can do is we can say V of C at a time is 0.3, 30% of our initial charge, initial voltage. So if we can take this equation, go and plug it into there, we can update our problem and we can effectively get rid of the VC at initial. So we're eliminating an unknown when we do that. And now we just have 0.3 is equal to e to the minus t over tau. And we'll just do some logarithmic algebra and just take the natural log of both sides, rearrange to solve for time, and these are our final time values here. This one here is put another star by it. This is an easy 5% if they give it to you on your exam. This is the one that I had you make note of on the formula sheet. So they want you to determine the capacitance of a parallel plate capacitor with plates 20 centimeters by 25 centimeters separated by that distance. Okay, so that equation for the capacitance is what we use to actually determine the capacitance of a capacitor that have two parallel plates. So it's C is equal to that epsilon, which is that dielectric constant that we talked about, times area divided by the separation distance. So if you go and plug in the 8.85 times 10 to the negative 12 farads per meter for the dielectric constant, you'll notice that there's meters right there. Well, these are given in centimeters for the area and millimeters for the separation. So what you'll need to do is go convert those values to be in meters. So when you convert those values into meters, it will cancel out this meters in the bottom of the dielectric constant. When you do that, it'll spit out your final value. On the test, you can either see this or that 8.85 times 10 to the negative 9th farads, or you can see 8.85 nanofarads. This is the same value, same answer. Okay. Okay. Here we have at time 0 a constant, so underline on constant, 10-volt source is applied to a 5 Henry inductor. So notice constant and Henry inductor. So those two values are important. Assume initial current for the inductor is 0. So initial current is 0. So we can grab that bit. Determine the current, power, and stored energy at times equal to 3 seconds. Okay. And something that you might be wondering is, well, how do I know to use the charging or discharging equation versus some of the other equations? Well, the charging and discharging equation involves you using tau, right? And tau here is L over R, but they don't give you a resistance value. So if there's no resistance value, you can't find this tau, so you have to use the other equations. Okay. So because this is an inductor, we'll jump to the right-hand side of that formula sheet. We'll grab this I of L equation. So 1 over L integral of 1 time 1 to 2, V of L d of t, plus I of L at time 0. So that's how you find the inductance at a time the current through an inductance at a time. But we said that I of L initially is 0, so we can just go ahead and send that to 0. And we can update our equation and start plugging in values. So I of L at 3 seconds will be 1 over the 5 Henries, 0 to 3 seconds from right there. 10 volts, constant, so there's no time element, there's no time variable in there. You can leave that. And then dt. All right. So all we got to do is do the quick integration. We'll pull that 10 out, so 10 over 5. Then we have the time variable, 3 to 0, 0 to 3. 10 divided by 5 will give us 2. Then 3 minus 0, so 6 amps at 3 seconds. Okay, and then so we've got the current now. Power, so P is equal to VI. So now we know the voltage is constant, so constant 10 volts. 6 amps, we solved for that earlier, so 60 watts at 3 seconds. Solve for that. W, remember W is going to be energy on the formula sheet. So it'll be 1/2 Li squared. So let's plug in our values here. And it will give us 90 joules for the inductor at 3 seconds. And kind of showing here how your inductors deal with current. So a lot of current things in here. All right, this one's not so bad. So here, let's, if I could get it to work. Okay, cool. I'll actually explain this one just a little bit more. Okay, so here, they want us to find the voltage V of A and I of A when the circuit is at steady state. Okay, but notice we've got a resistor, inductor, and a capacitor all in the same circuit. And we haven't worked any problems with that before, so that's a little concerning. Don't know how those all interact, but it's okay. Because of that phrase, steady state. Steady state is your friend. So if you can know how these elements interact at steady state, you're golden. So we see that here, initially, this wire was closed. Okay? So because this wire was closed for a long time, the current just sat here and loops around forever. It sees that there's a resistor over here, an inductor capacitor, there's a whole bunch of stuff. It just won't go over there. It'll loop around here forever because it wants to follow the path of least resistance. But once we open it up, now this acts open right here, and that acts open. So now the current has no choice but to come up and travel that way towards all these other elements. But if they want this at steady state, we need to take this circuit and redraw it at steady state to see how they're interacting. So if it's charging for a really long time, we know that the capacitor is going to act like a clipped out wire. It's going to reach a point where it can't accept any more voltage, it can't store anymore, and it'll clip itself out of the circuit. We look at the inductor. The inductor will reach a point where the current has been passing through it so much that it'll just turn into a wire. So we'll replace that in the circuit. So we come here and we replace where the inductor used to be with a wire. We replace where the capacitor used to be with clipped out. And now we just have current source, resistance. And we know that current can't travel down an open wire. So this current will just loop around through here. So the current I of A passing through will just be 2 amps. Okay. And we know that a voltage from our constant voltage along a wire is the same until it hits an element. So here, all has the same voltage. Then up here, all that has the same voltage. So we know this point, same as that point. This is V of A. This is V of A. So if we can find the drop across this resistance, I find the drop across right there. And I know the current running through it, know the resistance value. V is equal to IAR, 2 amps times 25 ohms, 50 volts. Easy peasy. Okay, so knowing what these do at steady state, super, super powerful. All right. Now here. We'll kind of talk this one a little bit more. Okay, so here we see that we have a big circuit. Voltage source, capacitor, 1, 2, 3, 4, 5 resistors, okay? First things first, let's go look at the switch. So looking at the switch, we see initially it's closed. So initially it's closed. Then we're going to open it up. We're going to hit that switch, open it up. Now it's open. Okay. So we know that operating initially at steady state, the voltage of the capacitor is going to have the same voltage as the source. So it's 12 volts. So that's a piece of information that we need. Okay. And they want us to find V of C at times 3.75 seconds. Well, that kind of is already indicating that I'm going to be doing a charging and discharging. If this is open now, this battery isn't supplying any 1, 2, 3, 4 resistors with voltage anymore. It's effectively not doing anything for the circuit. So because it's not doing anything for the circuit, I can just remove it entirely. Okay. So now what will end up happening is because this is doing nothing, this is the only thing that has voltage in it, this capacitance. So this capacitance is what's going to supply voltage to the rest of the circuit. But if I let it run forever, it's going to run to 0. So I let it run to 0. So now, looking at our charging-discharging equation, if we go through and just grab those voltages, so V of C infinity goes to 0, 0. We know initially it's 12, and we know the time, but we don't know tau. So when we simplify it down, we'll get V of C at a time is equal to V of C initial e to the minus t over tau. Now the only thing we're missing here is the tau. So we have tau is equal to RC for an RC circuit, so capacitor, resistance. But it's R equivalent. So we've got to combine all these resistors here to find our equivalent in order to use this. So what we're going to do is, like how we did in the Thevenin, and like we did earlier in the problem, we're going to find our equivalent with respect to the capacitor. So, respect to that capacitor there. So I see that initially here, these are in series. All right. So series 1, R series 1, 3 plus 1, 4. So combine those two to make 4. 2. So we got 4 and 2 are in parallel. Combine those down to get 1.33 ohms. And I combine that down, and I have 1.33 ohms. 3 ohms, 2 ohms, right there. And combine those three down. So just add those together, 3 plus 2 plus 1.33. And that gives me only one resistance value. So that is my R equivalent. So if I go and plug that into the time constant equation, tau is equal to RC, we get 1.0000033 repeating, which for our purposes is close enough to 1 second. So all we do is just take our VFC equation from up there, plug in all of our known values, and we'll find our final voltage value at 3.75 seconds. Okay, so I know I made a mistake and forgot to record the first time going through, so you didn't quite get the full step-by-step explanation of the entire way through, and I deeply apologize for that. I'll make sure it's actually recording next time. But of course, feel free to email me, ask me questions. You can leave comments if you want. I'll do my best to reply to those. I will be having office hours during spring break because I am the coolest SI that you know. Make sure to like, comment, subscribe, follow me on Facebook, Twitter, MySpace, Discord, AIM, all those good things. All right, everybody. Take it easy. Be safe out there. Talk to you later.